Let's begin lecture. Um, we have an exam next week and next Thursday. So you want to mentally start preparing yourself for that. And I know that at least one study group is formed that is oriented to office hours for me, for Caroline, and for Darien. And I want to emphasize the office hours. Caroline here to my right is going to be holding office hours on Monday afternoons, kind of late. So let's talk about the office hour situation. Okay, everything is in the Physical Sciences Building, PSB, and my office hours, I guess I'll turn this off. My office hours are, for this class, are 10:30 a.m. to noon on Wednesdays. And you just go in the main entrance, which is over here by where these people are standing. Actually, that looks like a fire drill or something. And then you go in the main entrance and then turn left. Now, Darien has office hours on Friday. And Caroline has office hours on Monday. And they're in the atrium. The atrium is the big open area when you first come in. And room PS 158 is the sunroom right next to the atrium. So you go in the main entrance and you turn left and look left, you'll see the sunroom PS 158, and that's where I hold my office hours. And studying with us is a very good idea because, I'm the instructor, of course, so that's your top opportunity. But then Caroline and Darian have been through this class and know the material and know how to study and prepare for my exams. Kind of like with Shai. She's got a different operation. She works for the SARC, and she has a different format. She doesn't have office hours. She has a particular method of presentation, but that's also a good study opportunity. And if you really want to get a good grade on exam 2, and if you want to be one of the people that get invited by me after exam 2 to be a special study group leader, for which the benefit is you get to skip the final exam if you do the things that I ask you to do as a special study group leader. Then you want to avail yourself of all the different study methods and techniques that we have. And here's a picture of Darien in the atrium. So that's what it looks like when you go in. It's really nice. Brand new building. It's really sharp and nice. Plus they have a soda machine and they have snacks, stuff like that. So if you need a Monster before you go to office hours, you can get one. But I noticed that they increased the price from $2 to $2.50 at these machines. Did you notice that? It's horrible. It's heinous. I mean, those things are expensive at the grocery store, but at school it's pathetic. All right, I want to go over with you, first of all, a little bit of extra reinforcement on the brain burner. I noticed that there was some action in the discussion areas in the past 48 hours or so when you were really bearing down on it. And I suggest that you all take notes, including the notes on the clicker questions, which are going to follow in just a few minutes. So let's take a look at this one. The basic specs for the coin were that it had a mass of 0.05 kilograms, 0.005 kilograms, and in the instance of homework 9 that I used, I came up with a speed V1 of 1.7 meters per second. Now, let me reinforce another concept concerning web courses. When you have a problem, a homework problem in web courses, and it's a calculation problem that you type in the number and then hit the submit key, those kind of problems are set to give you at least one random value every time you retake the assignment. So if you take all four attempts on an assignment, you might have 4 different values for V1, for instance. Okay, and I think that's the value that was randomly reset for each instance that you take the exam. And I bring that up because sometimes a student will work out the problem and then try to reuse the answer from their first attempt. And you might not be able to do that successfully. In fact, you probably will not be able to recycle it. You can recycle the strategy, but not the exact answer most of the time. Anyway, these are the specs. The environment for the coin is friction. There's some friction on the tabletop. There's also downward gravity, and there's also an upward rigidity force from the tabletop, but those two forces balance. The only unbalanced force is the friction force, and that is the one that opposes the velocity, and for that reason, it slows down the coin. And that is what friction forces always do. They're always opposite the direction of motion, or the direction, if you're trying to move something on a floor like a crate, and you're trying to shove it across the floor, and the floor's got friction, and the crate itself has got friction, it's not perfectly smooth, you'll be opposed by friction forces, static friction, even before it moves. Okay, and that is opposed to the push force that you apply. And then once you get it going, you have to keep pushing it or it'll stop because of friction. So there's 2 different kinds of friction: static friction before you break it loose, and then kinetic friction once you get it moving. Anyway, they're always opposite the motion. Now here's a vector to represent that. And this is the same diagram from inside web courses, inside homework 9. And I just added this friction force here in red to indicate that on this particular diagram, it's kind of a leftward force. Now, if you have something that's sliding to the left, the friction would be to the right. It's always opposite the motion. So once you've plotted in or made your own sketch of the motion, then you can think, all right, now my friction's got to be opposite that, and you just draw it in. Okay, so for this diagram, it's leftward, and because of that, if we do want to do any kind of numerical calculations, we want to be ready to use a negative sign to indicate the leftwardness of that force vector. And that's the unbalanced force vector that we've got. Now make sure you have all this jotted down along with the sketch, because I'm about to give you some clicker questions, and they're very, I'm not asking you for an answer, I'm asking you to think. All right, so I'm asking you to think about how to get to the answer. And that's a little bit more difficult, but I want you each to try. Okay, so make sure you have this stuff jotted down, just your basic specs, and then the friction force, and the direction, maybe the diagram. All right, so here we go. We're going to do some questions about the information that we have, and this is actually going to help you next week on exam 2. And on every exam, I like to have at least one brain burner. And one of the brain burners that you'll be ready for, or that I'll be ready to give you, is stopping force and Stopping force, stopping time, stopping distance. And that's what we're working on today. All right, so the next 3 questions in iClicker, I want you to make those part of your lecture notes. Okay? So as you see the question and think about it, I want you to jot down the options. Even though you're only going to choose one option, we're going to talk about all the options. And hopefully you'll choose the option that's correct, but you still want to know why the other ones are incorrect. Because if you can think about that in that manner, you'll more readily crush exam 2. Here's question 1. Let me start it. We're on frequency BB. Is it possible to figure out the slowdown acceleration for this coin? Go ahead and vote. And jot down the reasons. There's 2 yeses, there's 2 nos. One of them is a correct answer, and 3 of them are incorrect. So jot those down into your notes as you think. Notice how quiet it is in here. You can certainly talk, but whenever I hear the room quiet down like that, I know you're thinking. And that means I've got you right where I want you. Delaney, have you come to a conclusion? You and your panel of experts. I see you guys talking and discussing it. Have you got a conclusion? All right. Melanie, are you going to try Monday afternoon study session to coordinate with Kara? $30 for you to make your decision, and 30 seconds for you to jot down options A, B, C, and D. Oh, how I love seeing you guys think and work and discuss. Love it, love it, love it. 10, 9, 8, 7, 6, 5, 4, 3. Make your decision. 1, 0. All right, see what you guys voted for. Oh ho! You know, this is good. The correct answer is A. Make sure that you note that in your notes. And let me show you what you guys voted for. A lot of you voted for C. A lot of you voted for the other yes. Now the other yes down here, yes, because the initial velocity is specified. That one is, I can see that I tempted and nabbed a few of you because the initial velocity is specified. But that's not enough to get an acceleration. You need a delta V and a delta T if you're using the definition. But if you're using Newton's second law, you can use F equals ma and figure out an acceleration if you know the force and the mass, and that's what we've got. Option B, no, because the net force is unspecified. Is it really true that the net force is unspecified? Is the net force it's like saying the net force, you don't know how big it is. Is that true? It's not true? So you do know how big it is? How big is the net force? 0.01. And it's a negative value thereof to the left. That's your net force. That's the unbalanced. That's the only force that's not balanced. Okay, option D. No, because the final velocity, V2, is 0. That doesn't really have anything. You know, you can have any value of V2 and, compute an acceleration by the definition. Get delta V, whatever delta V happens to be. Now, if it's 0, that's nice. You can do it. But you also need a delta T, and delta T is not supplied in the initial information. Let's keep going. Question 2 for today. Will the generic distance triangle formula permit you to calculate the stopping time, delta T? Now this one again, I want you to add in your notes each of the options, because we'll talk about each of them, even if you answer incorrectly. Especially if you answer incorrectly. So read this and think about it carefully. Come down to the front and welcome. Welcome, Earthling. Oh boy. Thirty seconds. Jason, where are you at today? I don't see my bouncer, Jason. He's absent. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Did you get your answer in? All right, let's see what you guys have got. Uh-oh. Looks like we got some splaining to do. That's all right. This particular formula, 1/2 AT squared, yeah, you could use that for getting a distance, but only if you know delta T. We don't know the distance. So the answer to this is no. We don't know the stopping distance. If we did know the stopping distance, then we can figure out delta T. Now, let's take a look at some of these. Here's some of the other answers. A significant fraction of you chose option A, and another bunch of you chose option C. Let's look at option A. Yes, because acceleration can be calculated from the previous question. Yeah, that's true, but that doesn't necessarily give you delta T. The previous question uses Newton's second law, F equals ma. And that is not going to give you explicitly in itself a delta T. You can derive it from there, but not in itself. Option C was another popular. 14 students voted for that. Can you use that formula to calculate stopping time? Yes, because initial and final velocities are known. There's another one where, yes, it actually is true that you know final and initial velocities, but without knowledge of the acceleration itself, you're going to have a hard time figuring out how much time that took. And the last option, only one person voted for this. No, because the friction force is unbalanced. That has nothing to do with friction force is unbalanced. So that's a true fact. But that's not a reason to say no. That is, in fact, a reason to calculate everything and anything in this problem. The fact that you have an unbalanced friction force means that you're slowing down. All right, let's keep going. Let's go to question 3. All right, the generic distance triangle formula isn't cutting it. Not enough information. However, there is enough information to use this formula. And again, jot this one down. Or cheat and take a picture with your iPhone. That's not cheating. So you're using all your crafty skills. But definitely make a record of these concepts, A, B, C, and D. Thirty seconds. Boy, you type fast. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Whoa, look at this. Some people voted for A, some voted for D, and a few of you voted for B. Nobody voted for old reliable. What is old reliable? Pythagorean theorem. All right, so that's a spatial formula, so it's not going to get you a temporal piece of information. The correct answer is D, and 61% of you did vote for that. And think about it. We know the momentum. We know the momentum state, momentum number 1. We know momentum number 2, so we can figure out delta P. We know the net force, that's negative 0.010 newtons. So we can figure out delta T from that equation. And option A and option B, definition of acceleration, that's another one where we don't have sufficient information to get. Actually, we could use that. Now that I'm thinking of it. Hey, you know what, you guys? Option A is correct. Also, So I'm going to have to figure out how to give everybody option A points as well as option D. And make a note to yourself, the fact that there's two different ways to get this should indicate to you that old saying, there's more than one way to skin a cat. All right? And did you ever hear that? It's kind of disgusting, but I guess it's like from the 1800s they had to skin cats. I don't know. Anyway, there's more than one way to run an airline. Okay? Put it that way. All right, let's keep going. So let's look at this. Let's execute the strategy the way that I have it envisioned. And here's your strategy list. Go ahead and make a note of this. And even though you may have gotten a really good grade on the brain burner, your first try, go ahead and sketch out this or list out this basic strategy. First, we're going to get the acceleration using F equals ma. And then we're going to use the impulse equation with that to get delta t. And then we're going to use the generic distance triangle formula to figure out the stopping distance, because that's what you've got to do in some way. Now, there's a few people I noticed in discussion that posted an answer in terms of work and kinetic energy. But they were just using formulas. They found a formula and used it, but they didn't even say what it was that the formulas were about. We'll work on that today. But here's our strategy for now. Acceleration is equal to force, little f, divided by m, which in this case is negative 0.010 kilogram meters per second squared. That's a Newton. And then in the denominator is 0.005 kilograms. And one of the things that you can do now in your paper is cancel kilograms top and bottom if you desire. You can do it at any point that you like. It's a good point to do it. All right, now if you actually use your calculator, you better get your calculators out and double check me. Negative 0.010 divided by 0.005 works out to negative 2. Anybody verify me on that? Negative 2. So give that 2.00, 3 significant figures. And there's the acceleration. Now, if I knew delta t, I could use the distance triangle formula, but I haven't got delta t yet. To do that, we need to use the impulse formula. So now here for part 2, here's what I have for my net force, negative 0.010 newtons. And here's delta t. And notice that I have my negative signs in here. And that is to keep things squared away. The directions are important. Because you have left and right, significant things to the right, significant things to the left. So you better do it carefully. The other side of the equation, here's delta p, the change in the momentum. And the change in the momentum is just the mass, 0.005 kilograms, times delta v. And notice that this one is later minus earlier. V2 minus V1. That's the pattern for deltas. It's always later minus earlier. Delta V is V2 minus V1 in this case. And so that's 0 minus a 1.7. And notice that in this sub-calculation, this little part of the calculation, we get another negative sign. That is all right. So down below here, I've got my left side. This is the F delta T side. And over here, if you actually multiply that out, you get negative 0.0085. And the units there are kilogram meter per second. The units on this side are kilogram meter per second squared, and you also have a delta T that you're trying to figure out. Now that's going to have units of seconds, but it's still a symbol. We don't have a number to put in there, so we can't put the seconds units in there. But what you can do at this stage is cancel kilograms left and right, and you can cancel meters left and right, and you can cancel one factor of seconds from the left and one factor of seconds in the denominator on the right. And that means you'll only have seconds left over here. Or you could just divide both sides by this mess. Okay, negative 0.010 kilogram meter per second squared. And then you got per second squared in the denominator, a fraction in the denominator. And that means it goes around to the top. You know, division by a fraction is the same as multiplication by the reciprocal of that fraction. So that second squared goes up to the top. And when you calculate this one out, notice also in this one, I've kept my negative signs all the way up until this point, William. All right? And negative divided by negative is positive. Good. So my answer, even though I've got negatives floating around in different places, that works out to a positive number of seconds. And in this particular case, it's 0.85 seconds. Now I can use delta t in my acceleration distance formulas. And we're going to do that in just a second. Let me pause for questions, though, if you have one. Go ahead. There are two ways to do it. Yes. There's more than one way to, you know.
The first clicker question, it said, can we know it by figuring out the velocity? Would that be correct also?
But you don't know the delta t.
But there's enough information to figure that out.
Eventually, yeah, but not without using the impulse formula. Okay, think of it that way. So, in other words, I guess what I was thinking on that one, you can't use the definition of acceleration until after you've used impulse formula. Is that a good question over here?
How would you write out the impulse formula? Like, would you write out delta?
Okay, the question is, how would I write out the impulse formula? It's right here. See it there?
But how would you know how to do like the initial velocity minus?
That's in the given information. Yeah, you have to have a certain, the initial specs, and then the final spec is it's at rest, stopped, so it gives you V2, and then you can do it. Question up front here.
So, like, our main goal is to get the stopping distance, and so we're trying to get the change in time, which to get the change in time, we need to figure out the acceleration so we can plug that in so that we can use it.
Well, we're going to use, the reason that I wanted to get the acceleration was so that I can eventually use the distance triangle formulas. Okay? To use the distance triangle formulas, I also need the time, the stopping time, which I now have. All right? And so now we're ready to operate in strategy part 3. All right? So here's the third part of the strategy. And I've moved my delta t value down here to the left, just so I have it for convenience. Here's the formula that we're going to use. And we had it originally a couple weeks ago x subscript f equals x subscript I, etc., etc. But now, today, I'm restyling it with subscripts 2 and 1 so that it's x subscript 2, in other words, the stopping position, is equal to initial position x1 plus a distance rectangle here and an acceleration triangle here, and this acceleration triangle has a minus sign in it, right? And we're going to work that out. Question? I had the wrong numbers in the formula. Whoa. I did the... That's correct. That's correct. That's correct. And that's correct.
Yeah, that would have been 8.5.
Oh, okay, I see. So I dropped a 0 here. Okay, so this should be a 0.0085. And then this, all right. All right, thank you for pointing that out. So put an extra 0 in here. All right, let's get that distance calculated. All right, so as I said, here's the initial position. Now we're going to call that 0 because we could call it anything we want. It's not given, your starting point. It doesn't say x1 equals 0. It's at the 0 point of your system. It doesn't say x1 is equal to 5.5 light years or any other distance away from the origin. So we'll just use 0 there for convenience, and we'll figure out the rest of the distance from this distance rectangle formula and the distance triangle formula. And we've got everything we need for that. All right? Now, here's the initial speed, 1.7 meters per second. And here's the time, 0.85 seconds. All right? Now, if there were no accelerations, that expression would tell us how far it's going. But we do have an acceleration, and it's a negative acceleration, negative 2.00 meters per second squared. It's slowing down. All right? And so here's my 1/2, 0.5. Here's my acceleration. And then here's my time, my elapsed time value, 0.85 quantity squared. Now, if you calculate this one out and calculate this first term, or the second term here, this one is 1.445, and then the third term here with the acceleration is negative 0.7225 Sava. And so check this out. This is exactly half of this. That's the way it works out. And so your final answer to 4 significant figures is 0.7225. And on that homework problem, I asked you to give me 2 significant figures, 0.72 to the nearest 0.01 meters. Do you have a question over here on the aisle? Do you have a question? With the red hair and the white T-shirt? Yeah, you don't have a question? Okay. It looked like you had a question. Megan.
Is there an advantage to using different systems from this formula? Because I know when I do the calculation, I did all of the things I got the acceleration input formula, the delta t, and then I did the formula in order to get
1/2 AT squared.
sorry?
You used 1/2 AT squared.
1/2 squared.
Okay, Megan has asked a good question. She said, can't you just use 1/2 AT squared? The answer to that is no, not really, because our acceleration was negative. And that would give you a negative distance. All right? Now, it works out the same way, and that is because the path that this thing follows in time, Megan, is exactly the time reversal of a drop from 0 to 1.7 meters per second. All right? And that is why that formula works, but it won't always work depending on the question that I ask you. This formula will always be kosher. And it will always allow you to handle negatives and positives, lefts and right, with care and do so accurately. All right? It's not a flaw because you've got it down here. But my point is, so this is what you get from 1/2 AT squared. But Megan, to get this positive number, you have to get rid of this minus sign here. And that comes from this one right here. All right? And I chose to keep careful accounting of my left and right. So I could not drop that. Because I could not drop that, I had to use the full general formula up here. All right? Question in front. Okay. Any other questions before we continue? Yes, fire ahead. Because this one right here, this one, and this. That's what you're asking about. Because it's initially moving. It's moving at 1.7 meters per second before it encounters this force. Okay, so if you start your clock and the object is moving, you've got to use this term. You cannot ignore it. All right. So Megan, if I had asked you not for a stopping distance or stopping time, and you tried using that distance formula that you used, you wouldn't have gotten the right answer. The only time that accidentally works is when I ask a stopping distance or stopping time. Okay? But if you don't use that, then you're doing something that's not true. Because you are moving, and then you're losing, and the acceleration is cutting your speed away. And according to the distance triangle technique, this is the part of the formula that is decreasing the amount of distance that you travel. When you start out with, at 55 miles an hour and then hit the brakes, it's going to take you a few seconds to stop, right? But if you hadn't hit the brakes and you stayed at 55, those few seconds, you'd be way down the road, right? Right? So to accurately calculate your true position under stopping conditions or deceleration conditions of any kind, you got to use this, and you got to use minus signs. You got to do it carefully. And that is why this one is a brain burner. Now, you're going to have some homework tonight with some more brain burners. And I'm going to show you a more excellent way of tackling this problem that hopefully appeals to you a little bit more than this kind of tricky, complicated way figuring out delta t and all that jazz. All right. To do that, we have to talk about the four-dimensional structure of space-time. Now, do not lose your head like this guy. Check this picture out. See this guy? You know what that is? That's from refraction of light. Just like when you're out fishing and you try to poke a fish with your fishing pole, because nothing seems that you can't catch any fish, so you may as well try to spear it with your fishing pole, and it looks like your fishing pole bends as soon as it goes in the water. It's the same thing here. Anyways, let's talk about four-dimensional space-time. Now, this is the development, profound development that Albert Einstein made about 110 years ago, 1905. And he said, if you think of the universe as not just three spatial dimensions, X, Y, and Z, but time as a fourth dimension, and therefore as a dimension, part of a Pythagorean theorem, or something like a Pythagorean theorem, in other words, distances, calculate distances with time as well as with delta x's and delta y's and delta z's. He said, if you do that, it explains an enormous amount of physics that we can't explain otherwise. So Maria, in his view, to understand, he was always thinking about light, electromagnetic radiation, beams of light, at least to start with. And he said you can't really understand everything. Lots of things look like a paradox unless you take a four-dimensional view. Now, the other part that has to be partnered up with that is the dynamical quantities. In other words, we have positions, but because we are studying objects that can move, we also have velocities and momenta. Okay? And Einstein said the dynamical quantities that partner up with spatial dimensions are momentum. So momentum is a mass times a spatial velocity. In other words, you can have a velocity in the x direction and a little bit of velocity in the y direction, up and down. And you can even have a little bit of velocity in the z direction. So if I throw a baseball, or I don't have anything I can really throw up here, but if I had a Nerf ball, and if I threw it at a diagonal, if I threw it over to Celine, raise your hand. Okay, if I threw a Nerf ball to Celine, it would be, and if I threw it up to her, so over the first two rows, and then to Celine, it would be going up in the y direction, and it would be going away from me in the z direction, and over to the right side of the room, so it has some positive x velocity as well. So spatial velocity has x, y, and z components as well. The formula that we use for that is P equals mv. Now, that's for the spatial partner of, or the spatial quantity in dynamics. The temporal or fourth dimensional quantity in dynamics is energy. And that's one of Einstein's most famous equations. E equals mc squared. And when he wrote that one down, he revolutionized all of physics. And even in 1905, when he first wrote that down, they knew that if that was true, it would change things. And it has done so. And it has been verified very, very thoroughly. Matter of fact, those LIGO observations that we talked about last week were huge verifications of the theory of relativity. Now, let's take a look at the three spatial dimensions because they're going to be important for us. If you're looking at the lectern here where I'm sitting, then you could think of the x-axis is going off to the right and the left, and then the y-axis is going up along the wall vertically, like this. And then the z-axis, I don't know, kind of sliding in the direction of the aisle out towards you guys. All right, and so the momentum vector expressed p with a little arrow over the top is the scalar quantity mass m times the velocity vector, and the velocity vector can have an x component, a y component, and a z component. The energy is going to be only one number. It is not going to have components. Or you could say it this way. It is the temporal component of a four-dimensional dynamical quantity. And that quantity has a special name in relativity, for momentum. But this, here's the big LIGO device. Question? No, I can't go back. Grab it off the YouTube. Yeah. If you got enough, jot down. Remember, jot down enough so that if I go too fast for you, you can go and grab it off YouTube. All right. Now, this is a picture. This is out in Hanford, Washington, out in the big Central Valley of Washington State. And this is the 4 kilometers away is way up here in the distance. And these two jokers here are at like where the two tubes, there's another one outside the picture that's going off in this direction, I guess. All right. And those two, and they got a very special laser beam going right through the middle of that tube. And that's the one that picked up this gravitational signal. And none of this would work. None of this would make sense. This would be complete gibberish. We would have no idea what this was if we didn't think four-dimensionally. So write down to yourself in your notes, I have got to start thinking fourth dimensionally. And that is a big club. Every scientist is now challenged for the last 100 years or so to do that, me included. So let's talk about energy. And I want to start with this picture. All right, and this is a picture of a bunch of guys in a bike race over there in France, I guess, or Spain, up in the Pyrenees, or maybe up in the Alps. I've never been able to figure out where those guys are. But they're going uphill, these cats. And then here's their uncle or whatever in the car following, and they got extra water and food and whatnot, extra bikes. So you're going uphill, and you know you're one of these guys, and you're pedaling, right? And how do where does the energy come from that gets you uphill? Well, it doesn't come from looking at it. You got to actually use your muscles. Right? So step one, to go uphill, must exert muscle power. All right? And for those of you here in Florida that have never ridden up a real hill, it is not easy. These guys are really, really fine athletes doing this. Because they're gonna go up that hill. That's maybe about the tallest hill. To where they are right now, that's maybe the tallest hill in the Orlando area. All right? But those guys are going to go maybe another 2 or 3 miles uphill. And it's pretty challenging. And you can't do any of that, if you don't have any carbohydrates. You have to have some glycogen or some ketones if you're in ketosis. And where does the energy come from in food that you eat? You're having a smoothie, you're having some granola bars or something? Well, it comes from animals and plants. And of course, everything comes from plants because animals that we eat also eat plants. And where does the energy come from in plants? That comes from photosynthesis. All right. Sun shines on a green plant, and the green plant converts the sunlight and water into some sugar. The photons of energy provide the photons of sunlight from the sun provide the energy in the photosynthesis reaction. So photosynthesis happens inside the plant cell, all right? And the energy that drives that chemical reaction comes from the photons of light coming in from the sun. Okay, so all those nice green, red, yellow, orange, blue, indigo, and violet photons, they're driving the photosynthesis. And where do those photons come from? Well, they come from the nuclear fusion reaction in the center of the sun. So it's kind of cool. I mean, you're driving that bike uphill, and you get it. Your muscles are pumping, and they don't work unless you have some food. And of course, the food comes from animals and plants are at the bottom of the food chain, and they get their energy from photosynthesis, and photosynthesis gets its energy as a chemical reaction from photons of sunlight. And the photons of sunlight are there because there's big nuclear reactions going on in the core of the sun. So you could say that your bicycle is nuclear powered. So next time you're riding around and you're huffing and puffing, just say to yourself, this is a nuclear powered bike. I can make it. I'm going to make it. I have just like Doc Ock in what was that, Spider-Man 3? The power of the sun. So everybody, whenever you eat food, you're consuming the power of the sun. All right, energy. Here's a tank, World War II tank on the move. Energy is the dynamical quantity that encodes the changing speed. Not changing velocity, but changing speed. How does it do it? The way to get your mental energy around this idea of, or your mental concepts around the idea of energy, is to think about the path. And we've done this already when we talked about centripetal acceleration and centripetal force. We talked about a generic path. We're going to do the same this morning and finish on Thursday. For instance, on the path that you are following, is the force tangent to the path? Or maybe, in other words, is it parallel to the path, or is it maybe anti-parallel? Is it parallel to the velocity that you're going, or is the force, like a friction force, anti-parallel, opposite the direction of the velocity? Right? Legitimate questions. Another question, is the force that is giving you F equals ma on this path, is the force perpendicular to the path? And we know all about that. Uniform circular motion. The force that keeps you on that path at uniform speed is centripetal force. Okay, and this is the force that's at right angles to the velocity. Now, so you're thinking about the path and the relationship of the net force to the path. The other thing that you must do is partition the path into line segments. Now, there's two ways to do it. One of them is by clock. In other words, every 1 second of travel. Or think of it stroboscopically. Every flash of your strobe camera. How far did you go? And where is the line segment on the path between flashes of your strobe? The other way to do it is just by measuring out, and this is the way that the highway department does it out on the turnpike and the interstate and so forth. Mile markers. You've seen them a zillion times. You're driving to Miami and you're going past mile marker number 109. And then the next one, 1010 or 110, etc., etc. Now, those are two different ways to partition a path. And the different partitions temporal or spatial number, that should be A and B instead of C and D. Go ahead and change that to A and B. A is temporal, B is spatial, the meter stick, and delta S here signifies any change in position along some generic path. So that's a generic increment, spatial increment. It could be a delta X or a delta Y or a delta Z or something like that. Megan, did you have a question?
I was going to ask you delta S for spatial.
Yeah, delta S stands for some generic spatial increment. So, let us begin with a simple trajectory. You know, Galileo didn't know any basketball. But if he did, he would have thought a lot about vertical free fall of basketball. So that's what we're going to do. So let's do a temporal partition of this very simple trajectory. And I've mapped it out very carefully for 3 seconds. Starting up at the top at time t equals 0. Then 1 second later, I put a mark. And then 1 second later, my strobe flashes again, and I put a mark. And then 1 second after that, my strobe flashes again, and I put another mark. And after that, the 4th second, t equals 4 seconds, I'm off the charts here. I'm out of the picture. But the first 3 seconds we got up here. All right? Now, the temporal partition is delta t equals 1.00 second. Delta p is equal as well. And we have studied that. We studied that last Thursday. That every 1 second of free fall, the basketball acquires another, 1.58? Something. It acquired, no, I think we did smaller time increments last week. Anyways, every 1 second, a basketball will acquire the same amount of delta p as it falls downward. So delta p and delta t, if you do equal delta t's and measure the momentum, then the momentum will have changed by equal amounts. All right, now delta p is the dynamical quantity that's associated with the temporal partition. All right, and the temporal partition, delta t is your geometric quantity. So what we're trying to do is establish, according to the principles of Albert Einstein, a relationship between geometric quantities and dynamical quantities. And for us, the dynamical quantity is delta p, and the geometric quantity is delta t. Equal delta t's gives you equal delta p's. All right? So there's your temporal partition of the free fall trajectory. Now we're going to do another partition here. And this one's going to be the spatial partition. So go over here to the right and draw a copy. And we'll call the starting point y equals 0 meters. And then what we're going to do is let it fall 18 meters and make a mark on our vertical trajectory. Right? So now my bookkeeping is spatial. I'm keeping track and of the distance over here. Now over here I was keeping track of the time and making my marks on the trajectory according to what time it was. Over here I'm going according to the distance, how far down it is. Second partition, negative 36 meters. Another 18 meters negative, Alexis. And let's do one more, negative 54 meters. All right. That's not too bad. And my delta y, my geometric quantity is delta y All right? Now, the question for us is on a spatial partition, go ahead and make a note. This is the spatial partition. The same trajectory, we're just using different accounting methods. Okay? And if you're an accounting student, you know that there's different ways to write the books. And you know, sometimes it's easier to do it one way, sometimes it's easier to do it another way. And that's what we're doing. The question here is, all right, this geometric quantity, I've sliced up my partition into equal parts. Just like over here, I've sliced up my partition into equal time segments. All right? Now, I have a dynamical quantity that partners up with delta t. So what is my dynamical quantity that partners up with delta y, with this partition of the path? That is our critical question. Is there a dynamical quantity that has equal increments on this partition of the path? And if there is, that will be the space-time partner of momentum. Because we know what momentum is. Momentum is the equal increment dynamical quantity for equal increments of time. So for equal increments of distance, there's got to be some other quantity. In other words, if delta u is equal on this particular partition of the path, you know, what is u? Right? So there's another way. Go ahead and write down that sentence, that question. If delta u is equal for every 18 meters of drop, for instance, well then what is u? It's not mv, because we know what mv is. That's momentum. There's got to be some other quantity that works out to have equal sized chunks on a vertical trajectory. Either that or Einstein is a nitwit and he was wrong. But we know he wasn't. Very smart guy. The answer to this question is yes. There is a function u, and the fancy name for it is energy. Now, I'm going to go just a few more minutes, and let's push a little bit further. Now, we're going to make an analogy. The analogy that we're going to apply is an analogy to the impulse formula. Now, the impulse formula is all about, look at that, delta P's and delta T's. Nice. All right, so can we get something like that for energy? And hopefully it'll look something like this. F net times delta S. And in this particular notation, as I mentioned, delta S could be some generic displacement, like a delta X, a delta Y, a delta Z, even a delta R if you're moving radially outward along the radius of a sphere. All right, so hopefully this energy business is going to have a force times a delta S. Just like momentum, delta P, had a force times a delta T. So hopefully this will be useful for us. So go ahead and draw in a generic path for velocity and choose a dot and then write in a velocity vector. As you know, it should be tangent to the path at that point where your dot is. Here's my dot right there where my cursor is. Now, I want you to write down a proviso. The net force for this object, we don't really know what it is. I haven't specified it, but it might not be parallel to the path. It might be perpendicular or a mixture thereof. All right, so to give you a mixture, write in a net force vector like this. And I made mine straight sideways on a path that's kind of sloping upward. All right? Now, what that means is you've got something like a Maserati that's accelerating through the curves because you've got some newtons of force parallel to the velocity, and you've got some centripetal newtons that are changing the direction of the velocity. All right? So, let me dismiss you there. And hey, you guys, would you like to have no homework tonight? No homework tonight? Okay, no homework tonight. I'll see you on Thursday, and then we'll have some homework. You're dismissed. We'll finish this Thursday.